Mega Mechatronics.
Welcome back to the Mega Mechatronics Bootcamp series for mechanical engineering. We're covering topics related to materials, and we'll be looking at ductility and toughness. Speaking of ductility, we're describing the plasticity of the materials, the ability for that material to plastically deform, to permanently deform. Some terms related to the plasticity of a material: bendability, crushability, deformability, malleability, and ductility, of course. So looking at the technical term of ductility, that's the performance under tensile stresses, and malleability, the performance under compressive stresses. We're trying to crush it together. And highly malleable material would be something like gold, where you can keep pounding on it and crushing it, rolling it, whatever, till it's 1/1000th of an inch thick, which is about the quarter of a thickness of a piece of paper. You think paper's thin, gold leaf is much thinner. And the reason is the gold atoms stick together, pun intended. So, but ductility is the general term that we use to describe the plasticity of materials. Here's application of malleability, so we're crushing the material. You see an English wheel here, applying pressure between two rollers, and you roll that material through, and it does stretch it out as well a little bit, but you are applying a compressive stress to that material. So that fender he's working on started off life as much flatter, and you can see it's taken shape. That takes a lot of skill. Here's a rivet, and it's important that rivets don't fracture or break when they're put under a compressive load. You see, here's a side profile of a rivet, and you see there's a little die at the bottom, and we're hammering and we're deforming the other end to create a fastener. And rivets have actually been around since the Bronze Age, at least 2,500 years ago. And here's an application of rivets on a motorcycle chain. So each of those cross pins has been riveted in, and you see someone here is manually riveting a master link in there to complete the chain. And an application of ductility, here's a wire drawing process. So we're pulling some sort of wire. This is, the dies are, and the size of the material is quite exaggerated, but just trying to show you. So we're pulling it through. We're not pushing it. If we're pushing it, we'd be extruding it, but this is drawing. So as we pull the wire from a coil stock of a certain size, and we add some lubricant, pull it through a die, and we're stretching that material out. And it is cold working, that material as well. Here's another form of ductility, is stamping. So we have a flat piece of sheet metal, and then we put it in a die, and then those dies press together. You could see an example here of a side panel or aperture, side aperture of a vehicle, and it started life off as a flat piece of metal, and then it was stamped out and formed, and also sheared. You can see there's some shearing going on there. So we can derive a good idea of ductility from our tensile tests. So we start off here with a strain of 0, and then we pull it across until the breaking point, which is the percent elongation is the maximum strain if you were to take that off of the stress strain curve. But it's not a perfect measurement because it does depend on the initial length that you're using, because there's more change in the middle where it fractures than on the outside. So a better way to gauge ductility with our tensile tests is to measure the necking. So you see in A, it's quite brittle, there's no necking, no change. B is what we expect from a ductile fracture, and then C is like the ideal ductility example, the most ductile. So to calculate that, we need to find the reduction of area. So it's similar to the strain calculation where we're looking at the percent change in length. Here, we're going to find the percent change in area. So we're taking the change in area, we're going to divide that by the initial area to get our percentage change. So to find the change in area, we need to know the initial area, and we minus that from the ending area, and that gives us our delta change, and we divide that by the initial area, and that gives us a percentage reduction of area. So let's look at some examples of some materials and these parameters. So looking at 1141 steel, we're at 12%, 47% reduction in area. 4130 steel, 11%, 43%. They're pretty close, but you can see the 4130 is quite a bit stronger. You'd probably prefer that material over the 1141 because it has similar ductility and toughness, but it is quite a bit stronger. And 9255, that's a bit harder. It is very strong, but not very ductile. And then you see the 304, 431, huge difference. So I'm trying to show that the material alloy makes a big difference in ductility, and what makes an even more difference in ductility is the heat treatment to that steel. So looking at toughness, this is the resistance to fracturing or breaking, how it reacts to impacts, and what we typically see is the more ductile the material, the more tough it is. But not always. So low ductility, typically low toughness, but a better indicator is the area under the curve, looking at the stress strain curve. So if you're looking at the brittle fracture and you draw a straight line down where it breaks at the break strength, we can see the area there. And now if we take the ductile one and do the same thing, the material with more area will be more tough. So you see that ductile one's definitely more tough. Let's take another example, some stress strain curves here. So starting from the lowest toughness, just based on looking at the chart, we can sort of derive a toughness. So just looking at the area here, you can see B has the least amount of area. D, even though it is more ductile, it's not as tough as A, which is, you can see the strength really makes up for it. And then C, of course, is very tough, very ductile material. And to quantify ductility, we do impact testing. So here is a Sharpie with a C impact test. Pendulum swings down, hits the material, and then we're going to measure the back swing and see how much energy was absorbed. So if we were to free swing that hammer without the specimen not in the way, it would swing up to a certain distance. If we put something in the way, it'll swing through, break it, but that material would have absorbed some of that energy in the pendulum, that potential energy, and then it won't swing as high. And that's how we can sort of, that's how we get the amount of energy that it absorbs. Here is a very similar pendulum style IZOD test. And you can see the Sharpie on the left there, the specimen supported on both sides, and the striker comes right at the notch, right in the middle. And then we have our IZOD test where the specimen's supported on one side and the specimen's impacted at a different area. So let's take a quick look at this video from Materials 2000. Excellent YouTube channel. Here's a link. Definitely go visit and watch that full video. So looking at the specimens, there is a notch in there. The Sharpie and the IZOD are very similar. The IZOD is a little offset, so the one leg is longer, but other than that, dimensionally they are similar. Here's a close-up of a real Sharpie specimen. And we also want to examine the specimen after we fracture them. So you can see these two steels are the same composition at different heat treats. You can see there's a brittle fracture, it just breaks off and less deformation. And the ductile fracture, you see there is some deformation. And again, with this different test, you can get a good idea that the one on the left is brittle compared to the one on the right, because the one on the right didn't even completely break, and you see how the edges are rounded and folded up, so plastically deformed, and that absorbed a little bit more energy, we can guess. As well as this impact test, we can test manufacturing processes such as laser welding here, other types of weldings, heat treatments, and things like that, stress relieving. So we weld those together and we try them at different heat treats to stress relieve and make sure that we don't have any brittle welds or anything. So temperature does affect the ductility, and some materials experience a ductile brittle transition. Looking at an example here, the vertical axis is the amount of energy absorbed. Tougher it is, the higher it is. And then we have a temperature scale at the bottom. So you see up top the copper, it actually maintains its ductility across a wide range of temperatures. The mild steel, and you see the FCC, that's face center cubic structure, and then the mild steel's body center cubic structure. So that does affect this ductile brittle transition, where body center cubic structures exhibit this sort of phenomena. So you can see the mild steel right around 0 degrees, it starts getting more brittle, and the zinc and nylon are pretty brittle around room temperature. And we can take a look at this exotic material. You see it doesn't start losing mechanical properties until around 1,000 degrees, 1,100 degrees Fahrenheit, 500 degrees Celsius possibly. That's pretty high. That's a huge range. And that's why they use it in jet engines, F1 exhausts, and I've even designed some heat treat fixtures to heat treat some valve springs using this material exclusively. So that concludes our ductility and toughness video, and thank you for watching.